Hey guys, today's video is about Gini index. One of the important uses of Gini index is in decision tree. The first one is to select the attribute to split on. To be more specific, we select the attribute with the lowest Gini index. If you remember from previous videos, we actually select the attribute with highest information gain or gain ratio to split on. The reason why we choose the lowest Gini index is because the meaning of Gini index is different, but we'll talk about this in detail later. The second use is to find a better way to split an attribute. For example, the divorce rate has 3 values, low, medium, and high, and we might want to split the attribute into only 2 groups. There are 3 ways to split this attribute, and we again select the split with the lowest Gini index. Alright, so Gini index measures the impurity of an attribute. Intuitively, we prefer the pure attribute, so we want the Gini index to be as low as possible. The formula of Gini impurity is 1 minus the summation of Pj squared. Gini impurity here is not Gini index itself. It's kind of like entropy in information gain. D stands for dataset or an attribute. N is the number of classes in the target attribute. Pj is the relative frequency of class J. However, to measure the Gini index of an individual attribute, we use the weighted sum of separate Gini impurity. In specific, if attribute A has 2 classes, the Gini index of that attribute is D1 over D times the Gini impurity of D1 plus D2 over D times the Gini impurity of D2. D1 over D is the proportion of data belonging to class 1, and D2 over D is the proportion of data belonging to class 2. In fact, each class contributes to the Gini index of the whole attribute. So we have to do Gini impurity calculation for each class. However, because this calculation process, Gini index is biased towards multi-valued attributes, just like information gain. But Gini index is more interpretable. Before we look at an example, I want to first show you the pure attribute indeed has Gini index 0. So, a pure attribute may have multiple classes. The point is, every class must belong to the same class in target attribute. For example, if people who are students all buy a computer, then this class is pure. To keep it simple, we only look at a situation where the attribute only has 1 class. So the formula of Gini index becomes this. So D1 over D can be crossed out since it's essentially 1, because all the data in the same class of attribute A. Then, assuming all the data are also in the same class of target attribute, then Gini impurity of this class is 1 minus 1 squared, which is 0. Therefore, the Gini index of pure attribute is 0. In fact, Gini index ranges from 0 to 1. 0 means the attribute is perfectly pure. 1 means the attribute is perfectly impure. However, Gini impurity only ranges from 0 to 0.5. Remember, Gini impurity is a measure of impurity for a single class, and an attribute may have multiple classes. To verify, say we have 4 data in this class or dataset, and these tuples are in the class yes in target attribute, so the data is pure. The Gini impurity of this class is 1 minus 1 squared, which is 0. Therefore, a pure class has Gini impurity 0. Nevertheless, for an impure class, which has 2 in the class yes, 2 in the class no in target attribute, the Gini impurity is 1 minus 0.5 squared minus 0.5 squared, which turns out to be 0.5. And this is actually the most impure case we have. So now you see the maximum of Gini impurity is only 0.5. Just to remind you, this 0.5 means we have 50% yes and 50% no. since this is just the relative frequency of a specific class. Again, the Gini index is not equal to Gini impurity. Gini index of an attribute ranges from 0 to 1. 0 is the purest, 1 is the most impure. I know that's a lot to consume, so let's stop here for today, and I will make a separate video to go through an example. Thank you for watching my video and see you soon.